In this video, I'd like to talk about what happens when you apply an electric field to a material. Now, this is hugely important technologically in all sorts of engineering applications. It's also a huge research field, including here at the ANU. So all we're going to do here is look at a few cases of it. This is just touching the surface of a very big field. Now let's start off by thinking what happens to an atom, a nice symmetrical atom like this one here. Now what you have is a positively charged nucleus, which is actually much smaller to scale than this. It would be smaller than a pixel, and a large fuzzy negatively charged electron cloud. Now let's say we apply a voltage to this. What's going to happen here is, as we apply our electric field, positive charge is going to have a force in this direction. It's going to pull the positive charge, the nucleus, off to the right, whereas the electron clouds, the negatively charged, is going to be pulled to the left. Now normally it won't actually pull them apart, it'll just pull them a bit to the side, and then so the centre of the negative charge might be here and the centre of the positive charge is there, and so their mutual attraction is going to pull it back together until it balances the external force. Basically what you have is an atom where the positive and negative charges are now no longer centred in the same place. And we often draw it like this. We just imagine it's an elongated thing with plus at one side and minus at the other side. In a liquid, like water, things are a bit more complicated. Because in a polar fluid like water, the atom is not symmetrical. You've got molecules with the two hydrogen and the oxygen, and the charge is not evenly distributed. Now in normal water, a glass you might drink, the atoms and molecules are going to be randomly organised. So in some cases the hydrogen is going to be pointing up, some cases it's going to be pointing down. But let's say you apply an electric field to it. What's going to happen is they're all going to line up. They're all going to have the negative charges on this side and the positive charges on that side. So that's another example of a dielectric. So you can basically once again think of all these as minus and a plus that's separated out. Now what does that do at the bulk level? You can't actually see the fact that the molecules are lining up. Well, here we've got a large block of some dielectric material like water or many polymers or things like that, and we're applying our electric field. And what you can see is for each atom, the positive charge moves over one side, the negative the other. If you take some bit in the middle of the block, you see the positive and negative charges cancel out. The only place they don't cancel out is right at the edge. So the net effect is, when you apply the electric field to a dielectric, you get a thin layer of negative charges along one side, a thin layer of positive charges on the other side, and everywhere else it cancels out. What this means is, because you've now got positive charges on here, negative, they're going to apply an electric field back in this direction. It's not going to be as strong as the electric field you're applying, but it will partially cancel it out. So what that means is, when you get a dielectric and put it in an electric field, the electric field inside is reduced. That also means the voltage between here and here is reduced, because voltage is just electric field times distance, less electric field, less distance. So you still get an electric field inside these things, it's reduced a bit. Now that's what happens if you apply a small electric field to something. What happens if you apply a large electric field to something? What you can get is breakdown. It's like bolts of lightning crashing through. What happens, you might think that if you apply enough voltage, you actually can rip the electrons out of the atoms. And indeed that can happen, but usually horrible things happen long before that. It turns out that in air and most substances, there are a small number of free electrons. In the air you're breathing in now, mostly it's neutral, so mostly the electrons are attached to the oxygen-nitrogen atoms, but there'll be a small fraction of ions and free electrons wandering around, often caused by background radiation or cosmic rays. But you don't need very many. Just have one free electron, and you apply a big enough electric field, that electron will accelerate, go faster and faster and faster. And if it gets enough room to accelerate, which means that it has to be a fairly low density gas. If it's too dense, it crashes into something before it's had much chance to accelerate. It's like you need a lot of room on a freeway to drive really fast. So if you've got enough room, that by the time the electron hits another atom, it's built up a huge speed, and when it crashes into it, it can knock some more electrons out, maybe 2 electrons out. And once again, if there's enough room, they will accelerate like crazy, so by the time they hit the next atoms, they can knock even more electrons out. And so what you get here is a cascade. You don't need very many electrons to begin with, only a tiny number, and there's always a tiny number present in the real world. What you need is enough voltage and a low enough density and a high enough voltage that the amount they accelerate before they hit something on average is enough to give them energy to knock more electrons out. That, it turns out, for air is about 3 million volts per meter. That's what you need to produce sparks, to produce lightning bolts and things like that. It's also a practical limit to the voltage we can use in power sources. There are many reasons why you'd like to use really high voltages in, say, powering your house and power lines, because if you have a big enough voltage you get very small losses. But if you have too much, you're going to get breakdown, you're going to get sparks carrying the electricity from one place to another and burning and destroying things in the process. So this is a fundamental limit to almost all electronic components. Now let's think what happens in a conductor. Now, conductors, like a piece of copper, have free electrons. Electrons are not bound to an individual atom but can wander around freely. That's what makes them a conductor. Once again, if you apply an electric field, the electrons will start moving, and they'll get some distance before they hit something. When they hit something, they'll bounce off and then hit something else and then bounce off and so on. And this is what produces Ohm's law. The larger the electric field means the larger voltage. Larger voltage means the electrons accelerate faster until they hit something, they accelerate again and accelerate. And so you end up with a steady stream of electrons bouncing their way down through the atom, and that's the current. How fast do the electrons actually move on average in a piece of copper? Well, actually, it's very slow. It's millimeters per hour. That's not the speed of electricity. When you apply an electric field, let's say you have a wire, it's not as if the electrons start at one end and then slowly work their way down to the other. The electrons are all there already. And when you apply a voltage, they all start to move simultaneously. So it's a bit like having a traffic jam and someone stands out with a loudspeaker and says, "Okay, everybody drive forward," and they all start moving at the same time. So that's the speed at which an electric signal moves, but the electrons are going much slower than that. A funny side effect of this is that you don't get any electric fields in a conductor. Let's say you have a piece of metal, a nice good conductor, and you apply an electric field to it. The electric field here is going to push the positive charges this way and negative charges that way. In practice, it's electrons going this way in a metal, but if it was some other sort of polymer, it might be positive charges moving around. And they will keep moving until you have a wall of negative charges along the side and left behind a bunch of positive charges along that side. Now, if it was a dielectric, they'd cancel out some of the electric field in the middle, but this is not a dielectric, this is a conductor. If there's still some electric field inside, the electrons are still going to be accelerated. They'll keep on being accelerated to this end until there is no more field inside. If there was any field left inside, they would still be moving. So what you get is when you apply an electric field to a conductor, you get a wall of negative charge on this side, a wall of positive charge on this side, and no electric field inside. The field caused by these charges has cancelled out the field caused by that charges, so there's no electric field inside. This is the science behind a Faraday cage, protection from lightning. If you're completely surrounded by a conductor, so let's say you're in a car, it's a very badly drawn car, give it some wheels, and a bolt of lightning hits, you're not going to get electrocuted because it's applying an electric field, let's say this direction, which will cause in the metal shell the positive charges to move up around the top and the negative charges to move around the bottom, and so the electric field inside will be zero. So that's a taster of what electric fields do inside materials.